Okay, hello everyone. Going to talk about some triangles, some ratios, and the Pythagorean theorem. They are immensely important in so much of what goes on in physics and in mathematics in general. There's a lot of great use for the Pythagorean theorem, for ratios involving similar triangles, and what we see with similar triangles in general. There's just a lot to do with the ratios, and studying the ratios associated with similar triangles can get us actually a derivation of the Pythagorean theorem. There are a number of derivations of the wonderful Pythagorean theorem. Using similar triangles can help us get there. The topic of conversation today, the topic of the lecture today, is similar triangles, ratios, and the Pythagorean theorem. I am going to take I've already kind of worked this from previously, but let's go into the plane of the blackboard and draw two lines that stay in the plane of the blackboard. If the two lines tend to get closer to one another, if one or both kind of veer closer to one another as they progress, on the other direction, they will tend to veer away from each other. But either way, if they tend to get closer at some point, in some place, if these were about to turn inward this way, they would intersect, and out here, as the lines go out, they get further apart. If you were trying to see the distance between the lines, draw some kind of segment between them. They get further apart this way and closer together that way. If they were bound to be intersecting. Parallel lines in the plane stay in the plane, and parallel lines in the plane stay in the plane, and they remain the same perpendicular distance apart from one another. Draw a perpendicular here. The perpendicular distance is whatever it may be, but that is a perpendicular distance. Draw the same, so draw a perpendicular distance between the two lines, and you get a particular distance D. If you draw a perpendicular distance down here between the two lines, it is the same length, D. The perpendicular distance, D, is the same no matter where you draw the perpendicular line. Well, draw two perpendicular lines somewhere. Draw two perpendicular lines somewhere, and on the outskirts of all that, you've got some kind of a rectangle. It may be a square, it may be just, my intention, it looks kind of like a rectangle right there. It wasn't really my intention, but you can get something that can look like a square as a rectangle, or you can get it to look like a rectangle the way it does right here. This is a rectangle, it's definitely not a square, as we're observing this. If this is, you draw some kind of rectangle. If it's a rectangle, draw a transversal going right down. Draw a transversal, a line going on forever in each direction, going right through or right with. This is the diagonal of the rectangle. Draw a line completely on top of the diagonal of the rectangle. Draw it all the way through. And here you got 90 degrees, 90 degrees, 90 degrees, 90 degrees. You drew the right through the diagonal. Just draw the diagonal that way and just have it extend that way. It's transversal. Well, this and this are congruent to one another. This is congruent to itself. Rectangles have the sides opposite of every rectangle are congruent to one another. So these two are congruent to one another. These two are congruent to one another, and this is congruent to itself. What does that mean? Well, they all line up. If you were to pick up one of these and arrange it the right way, you can put it right on top of that one. So what you got is we've got this guy right here, and we got this one right here. As we said, how they look. We could also use the postulate side angle side. This is 90 degrees. That's 90 degrees. That side's congruent to that side. And this side is congruent to this side. And so, okay, as we said, that side's congruent to that side, this side's congruent to this side, and this angle is congruent to that angle. So side, angle, side, side, angle, side. Side, angle, side, side, angle, side. These are congruent to one another. If they're congruent to one another, this is a 90-degree angle, and this is alpha right here. And this is alpha right here. This one right here would be 90 minus alpha. Well, actually, let me not even go there. Let me not go there right now. That's too premature, if you ask me. If this is alpha, then let's call this one beta, and we know that alpha plus beta are 90 degrees. If you want to use radians, use radians. I guess a lot of times for discussion of angles and triangles, at least initially, it's nice to talk about degrees. They're just a little easier to visualize than radians. But radians are the best to work with if we're working with Taylor's formula. Some of the great, some of the great expansions associated with Taylor's formula, you're going to be using the radian to take care of some of that. But that's this right here. All right, well, we said they're congruent, so if that's alpha and that's beta, what's opposite the beta is the length, is the side associated with these three hash marks here. What's opposite beta, so that's the same thing here if we're talking about them being congruent. And what's opposite alpha is the single hash mark, and so that would be alpha 2. And they add up to 90 degrees in both instances. They're totally congruent. Well, what's going on here, guys? This right here is an angle. This right here is also an angle. They're congruent to each other. They're equal to each other. And they're in the interior of these two parallel lines, and they're on either side of the transversal. They're called alternate interior angles. Alternate interior angles are congruent. These two alternate interior angles are congruent to one another, equal measure, and these two alternate interior angles are, let's back up on that one. These are definitely congruent to one another. These angles are not alternate interior angles because the way it was set up, for them to be alternate interior angles, you guys, we're talking about something like this, and it's on either side. So you got this, you got that. What about this? Can we also draw a conclusion here? Well, I'll tell you what I'm going to do. If this is beta, and this right here is 90, from here all the way to here is beta plus 90. And if this is beta, and this whole, if this is beta, and this whole thing is 90, this thing right here is beta plus 90. So, that right there, which is beta plus 90, because here's the beta, here's the 90, and the whole thing is beta plus 90. Here's the beta, here's the 90, and this is beta plus 90. Well, beta plus 90, whatever it may happen to be, is the same as beta plus 90. So what you have here is, this is an alternate interior angle, and this right here is also an alternate interior angle. So whether you're talking about the alphas being alternate interior angles and being congruent to one another, or the beta plus 90s being also genuinely alternate interior angles, they're also congruent to one another. So alternate interior angles are congruent to one another. Okay, so what? Where are we trying to go with this thing when we're talking about it? Well, let's say some more and let's draw some conclusions, I guess you could say. If this right here is alpha, if that's alpha, and that's beta, there's a number of things we can say here to figure this thing out. There's very much we could say. Actually, I don't know how wise it is to try to say all of it. But if this is alpha, and this is also alpha, then, it kind of get rid of this one, even though that's part of the transversal that was here. I just don't want to look at it here. You don't want to look at it right now, but it's going to fire out that way. But for right now, let's just look at what's happening here. If this is alpha and this is alpha, then this right here is so basically what we have here. If this right here is alpha, and that's alpha as we've proven, alpha plus whatever this is a whole entire straight line. It's an opening of 180 degrees. This is 180 minus alpha up here. Okay. Sure. Okay. Whatever. I mean, so if that's going to be this is the 180 minus alpha, then this right here, this one right here is also 180 minus alpha. I say, well, wait a minute. What are you talking about? Didn't you say it was beta plus 90? Yeah, I did. But aren't alpha and beta added together 90? Isn't beta going to be 90 minus alpha? If this is 90 minus alpha, beta plus 90 is 90, beta is the 90 minus alpha that we did, because these are complementary angles to one another. If this is alpha, this is going to be 90 minus alpha. And we played that game here and got this. This right here plus 90. Well, what's 90? What's 90 and 90 minus alpha? It's 180 minus alpha. So, guys, there's so much chalk here, guys. I don't know. I got to stop it at some point. But this right here and this right here are called vertical angles. This measurement this way, 180 minus alpha, is the same as this measurement right here, which is beta plus 90. Better put, 180 minus alpha. 180 degrees minus alpha. 180 degrees minus alpha is equal to 180 degrees minus alpha. These are vertical angles. This one right here then, 180 minus alpha, 180 minus alpha plus alpha is the 180. We make the whole thing a straight line. 180 degrees minus alpha plus alpha is 180. So wait a minute. The alpha and the alpha, these are two vertical angles. They call these vertical angles that are opposite each other like this. I mean, directly opposite each other. Here, they're alternate interior angles, and they're congruent. Here, they're alternate interior angles. The beta plus 90 and the beta plus 90. The beta plus 90 and the beta plus 90 are alternate interior angles. Beta plus 90 is 180 minus alpha, so 180 minus alpha, you can say as well, is congruent to 180 minus alpha. Alpha is congruent to alpha. Makes sense, because alpha plus 180 minus alpha will give you the 180, and that is a 180. Alpha plus 180 minus alpha will give you the 180. So 180 minus alpha and 180 minus alpha, alternate interior angles, are congruent. Alpha and alpha are, so these two alternate interior angles are congruent. These two alternate interior angles, call them beta plus 90 and beta plus 90, or maybe a little more intuitive to look at. It's the supplement of alpha for each of those. So beta plus 90 is 180 minus alpha. Beta plus 90 is 180 minus alpha. These two alternate interior angles are congruent, always are, and these two alternate interior angles are congruent. These opposite each other, they call these vertical angles. They are congruent to one another as well. So you're doing a lot of stuff to kind of make sense out of this. Now you might ask a couple questions. What's what the heck is going on here in relation to that? Notice I looked at the 90-degree angle not within the triangle, because right now I'm going to pretend I don't know that there's 180 degrees in a right triangle. Not only in every right triangle, but in every triangle period, there's 180 degrees. But I didn't know that. I don't know that yet. I got to prove that. So I'm looking at something like this, And well, I've said quite a bit, obviously, but what do you think we can say vis-a-vis some of this stuff that we have said? Well, in relation to this, see if we can say something else other than that. I think we just did say it, but just by virtue of congruence, guys, we're able to do it. They are congruent to one another. For the rectangle, it's a 90-degree angle, 90-degree angle, a third 90-degree angle, and a fourth 90-degree angle. There are 4 90-degree angles. The total angular measurement within the rectangle with 4 90-degree angles is 360 degrees. If you cut that rectangle to have two congruent triangles, just take a walk around and see what you got. This is beta plus alpha, that's 90 degrees. This is 90 already. This is beta plus alpha, another 90 degrees. This is 90 degrees. So we said, here it was, you took a walk, beta plus alpha, 90 degrees. Here's 90 degrees. Here's beta plus alpha, another 90 degrees, and here's 90 degrees. Well, they're all going to add up like that. We know that within the right triangle, it's for either one of these, we can see that the angles are the same. You got beta, alpha, 90 degrees. You've got a 90-degree angle. You've got alpha plus beta. You got a 90-degree angle. You got alpha. You got beta. Yeah, you got 90-degree angle. You got alpha. You got beta. You got another beta, and you got another alpha. There's a 90, there's an alpha, there's a beta, there's another beta, there's another alpha, there's another 90. So wait a minute, are you telling me if you double these, 360 degrees? Yeah, we said the whole, divide it by 2, 90 degrees plus alpha plus beta is 180 degrees. Every right triangle must have 180 degrees. These are all 3 sides, all 3 angles. The right angle, the 90-degree angle, there's alpha, there's beta. 90 degrees plus alpha plus beta, 90 degrees plus alpha plus beta is going to give me the 180. Yeah, we just did the math, we got 180, and wait a minute, the 90, the alpha, and the beta are all the angles in this right triangle. In fact, they're all the angles in any right triangle because I didn't specify what alpha and beta are. It'll work generally that way. Well, that's pretty interesting. Is it true always that it's going to be that way? Well, for everything, I mean, it is true always that it's going to be that way for right triangles, for every right triangle. What about here, the measurement of all these when we're doing something like this? So let me see here, guys. It's almost better off erasing it. We figured out who's who. Let me try and figure out what I'd want to say beyond that. Actually, you know what? You can kind of get yourself out of the woods pretty well here. For this triangle right here, we can get ourselves out of the woods pretty good here. Let me erase some of the stuff that we already know and already worked with to get to where we are. And let me see what I can do here. Let me see if I can kind of tinker with it on this side and kind of hold on to some things here that are of use to us. We know there's a 90-degree angle there and 90-degree angle here. 90-degree angle there, 90-degree angle here. This is alpha. I'll make it a little bigger, I guess. I don't know. That's alpha. That's 90. That's beta. Okay, we've already delivered that speech. If this right here, let's see what we can do here. So there's the alpha. There's the beta. It's just this. Okay, I'm kind of running out of Greek letters here, guys, in a sense. Let me see. Tell you what, we said it's a 90. We said there's 180 degrees. Alpha plus beta plus 90 is 180 degrees. Here's another right triangle right here, and there's a 90-degree angle in it to prove that it's a right triangle. Let's put this guy and call him, let's call that gamma, and we'll call this one there's delta. So this thing is gamma. This thing is delta. And what conclusions can you draw? Well, we already said a couple things, guys. We said that you add up the right triangle, the degrees in a right triangle, they're going to add up to 180. Well, here you go. Here's your 90. Here's gamma. Here's delta. We concluded that the letters were not specific. This alpha and beta could have been x and y, could have been theta and phi, whatever. The arguments that got us there are what get us there. That's the big thing. Same thing. Okay, what's going on here? Well, this is kind of weird, but let's just do it. Here's an angle, here's an angle, here's an angle, and here's an angle. 3 angles. They add up to 180. Here's an angle, here's an angle, and here's an angle. 3 angles. They add up to 180. Why don't we add 180 and 180 and get 360? Well, why don't you add this and that and get 360? Well, let's add them together. Let's add the left-hand side over here with the left-hand side over here. You've got, let me see exactly how we want to talk about it. Let me, let's talk about an important point. Get something that stands out pretty good here, guys. There's so much chalk here, I'm not sure what's going to stand out. The beta and the gamma put together are going to give you this angle right here. The beta and the gamma put together. Beta and the gamma put together are going to give you this angle. This is alpha. It's part of the small right triangle, but it's also part of the big general triangle, this whole thing. So the alpha is in the corner here, is part of the right triangle, the small right triangle, but it's also part of the big triangle. Delta is part of the big triangle. This angle, that whole angle, and that angle right here, I'd like to know what it adds up to in a general sense. Well, I'll tell you what. Why don't you add this angle, this angle, this angle, and that angle, and then tack on 90 and 90. And we already know that for this right triangle, this 90, this alpha, and this beta, the 90-degree angle, the alpha, and the beta add up to 180 degrees. In this triangle, same argument, the 90 plus the gamma plus the delta add up to 180 degrees. So when I add those together, let's add the 90, the alpha, and the beta, and let's add the 90, the gamma, and the delta. And when we do that, you know it's going to, these three add up to 180, and these 3 add up to 180. So this 90 and this 90 is a 90-degree angle. It's a little awkward. It's just, soon I'm going to just get rid of that post right here. I'm going to get rid of this particular line segment. It's not going to matter. But for right now, it does. 90 plus alpha plus beta, that's 180. 90, another 90 now. 90 plus alpha plus beta, 180. Another 90 plus gamma plus delta, another 180. Well, let's add them together. Let's see what I can say here, guys. I'll just put them in some kind of order. I'll go 90 and 90. whole bunch of stuff here, guys, what the order is here. Let me just figure out how I want to do this. I'll just put them right one on top of the other, I guess. I'll go 90 degrees plus alpha. You know, I want the beta and the gamma to somehow be pretty close together. So you're going to watch what I'm about to do here. I'm going to switch the alpha and the beta, the order of the addition. That doesn't mean anything. That's 180. Then I'll deal with this guy. 90 degrees plus gamma plus delta equals 180. So these two equations, the same two equations that were right here, right next to each other, I just put them one on top of the other. Now what I'm going to do is, guys, give myself a little bit of room. Number of ways to proceed here. Moved what I got to move. Luckily, I always forget. You guys have the feature of being able to reverse this stuff, which kind of works out great if we need to do it or speed things up. So you got this right here. Now, let's add these two equations. Let's add these two equations together. 90 and 90. 180. Beta plus gamma. Purposely did that. These guys right here, beta plus gamma. Why did I put them together like that? Because beta plus gamma is one big angle. What's the one big angle? The one big angle is the one big angle here, up here, beta plus gamma. Here's delta, here's alpha. Let's see what happens. Plus alpha, plus delta, 180 and 180 added together is 360 degrees. Subtract 180 degrees. Subtract 180 degrees on each side. Beta plus gamma, treat that as one angle, because it is. Here's one angle. Here's one angle. I subtracted 180 on each side. I got 180 degrees. It doesn't matter if it's not a right triangle. Any triangle has 180 degrees. It doesn't matter that it's not a right triangle. It does not matter that it's not a right triangle. Every right triangle has 180 degrees. Agreed. Playing games with non-right triangles, all other triangles basically, we can take any triangle and cut it in the right way, drop a perpendicular, and you can make every right triangle into the composition or the, you could take any right triangle and make it two right triangles pasted together. And in fact, you can take any non-right triangle and cut it in the right way by dropping a perpendicular, and you can make it a composition, a pasting together of two right triangles. Here are two right triangles that we had, guys. It was a downright mess. Yeah, there's two right triangles. I tell you what, let's take the artistic license . Here's beta plus gamma, whatever it is. Here's alpha. Here's delta. You add them together. Beta plus gamma. Here's alpha. Here's delta. You add them together, you get 180 degrees. So that's useful. So we know that all triangles, right triangles and all other triangles that are imaginable, all have degree measure total in them of no more or no less than 180 degrees. Any triangle in the universe of triangles has 180 degrees in it. No more, no less. 180 degrees in it. Every triangle, right triangle and non-right triangle, all other kinds of triangles, all triangles, including right triangles, but all other triangles, can be broken up into two right triangles. And then those two right triangles can be pasted together, and we can do various things and analyze various things regarding what we're doing. So there's a lot, there's a lot of analysis that we can do by being able to break up triangles into a composition of right triangles. Every single triangle can be broken up into a synthesis of two right triangles, in a sense, a composition of two right triangles. Okay, so you're wondering, okay, we know that everything we're going to add, all the angles that we're going to add are going to be 180 degrees. So what would you say on this stuff? Are there some conclusions we can draw? Are there some things we can say? Well, I've done this in other places. I did it in at least one class one time beyond this a little bit. Let's talk about this and see what we can say related to ratios, related to similar triangles, and what kind of arguments we can make. Okay, so essentially, okay, well, some people say, okay, not a big deal. So what? Well, I'll tell you what. If you had, much can be said here. So let me try to think exactly how I want to talk about it. There's different ways I've drawn some of this stuff in the past. It should come out either way pretty good for us. Let me draw this. It's actually a pretty big triangle. There's an angle theta here. So if I put any right triangle inside of here that has the attribute of having an angle theta in it, in addition to a 90-degree angle, well, we know that if this is theta and this is 90 degrees, this is 90 minus theta, because altogether they got to add up to 180. If I give you any 2 degree measurements of any right triangle, you know what the third one's going to be. If I give you that it's a 90-degree angle inside of the right triangle, obviously it is, by definition. It's a 90-degree angle within the right triangle, and there's an angle theta, then the other angle is locked in to 90 minus theta, because 90 minus theta plus theta is 90, plus 90 is 180. So if I get a smaller triangle that's a right triangle and has an angle theta in it, and I put it in the corner here, and it's got an angle theta to it, and I draw it here, if that's 90 degrees, if that right there is 90 degrees, 90 degrees, here's theta, this is 90 minus theta, just like that's 90 minus theta. Okay, and we also see that they're corresponding angles, so they'd be congruent. We proved that earlier, but we proved a number of things earlier, actually. So we're doing pretty good. So if you're looking something like that, and then you wanted to say stuff, now here you could say, well, if this was a number line somewhere, and x is the horizontal, and y is the vertical, you could say this looks a whole lot like y equals mx plus b, or y equals mx. Let's say that corner right there is x equals 0 to make things easy. If that's the case, you could say that, if there's like where to go on this, guys. I'm trying to just figure out where I would actually want to put this. If you were to say this is, a lot of ways to go here, guys. I drew it the way I drew it. Let me stay with it. Let me say this is length A. That's length B. And I could say, go all the way across to here, make a 90-degree angle with that. There's a lot of questions to ask here. If this is, if I go all the way across, hit it perpendicular, that's a 90-degree angle. This is not, we already said this is 90 minus theta. Here's a theta for you again. Here's theta for you again. So you could say a bunch of things that way. You could also say that, you could call this length right here. I did it a little differently, I think, when I did it another time. It doesn't matter. The basic concept is you got this here, and that's y. What does that mean? Well, it means a lot of stuff. It means that if you go here, the whole length here, that's a, that's x. The long one right here, guys, is a plus x. It's one of the worst drawings I've made today, guys. I'm sorry, but there it is. That's should not stay, actually, guys. It does not look good, but you know where I'm going. That's x. Okay, so that's x, that's a, that's b, that's y right here, that's b right here too then, right? I mean, that's the congruence associated with the right triangles. Forgive me. So the congruence associated with rectangles on this, and this would be y plus b. You're probably wondering, okay, what is he talking about? Why all this? You know, well, that's pretty big here. That's pretty. There's a hypotenuse here, guys, and there's yet another hypotenuse over here that's really, really big. The whole thing is a hypotenuse. This has a hypotenuse associated with this right triangle. This right here has a hypotenuse associated with this right triangle. And the whole thing, the whole big thing, has a hypotenuse associated with the big right triangle. Well, you know, we talked about what's going on here, guys. And these are, in a sense, we're going to prove a couple things here. Now, I did say something about y equals mx plus b. You know, you're tempted to think, and you'd be right in thinking so, but it's not something, maybe not in the more, it's not really discussed in the most rigorous of fashions sometimes when it's discussed. If you say y equals mx plus b, that really describes so much of what you do in ratios. You're comparing things vis-a-vis how they would look. You're comparing so much of what you do in ratios, you're comparing them as to how they look on triangles. It's a big thing. It's not the only thing, but oftentimes when you're talking about the rise over the run, here's a rise of y plus b, and it occurred after a run of a plus x. There was a total run. There was a total run of a plus x, and then a total rise of y plus b. Here there was just a total run of a and a total rise of b. Here there was a run of x and that. Well, look, these are similar triangles. These are similar triangles, guys, because the angles, they have the exact same angles. All the triangles under consideration here. The very biggest triangle, the smallest triangle, the triangle kind of in the middle in size, they all have that. What does that mean? Well, if you took the rise over the run, y over x, we're going to show that y over x is the same as b over a is the same as y plus b over x plus a. And you think, okay, well, that's obviously provable with this. Yeah, you could say so if they lie in the same line. A lot of times this, you know, in my judgment, and perhaps I'm being too dramatic about the whole thing, that's not always obviously shown that it's actually going to lie on a straight line. It does look, if you go, the more you walk this way, it maps into mx. The more x values that you're getting here, they'll map into y values according to this formula, y equals mx. Be the first one to agree with that. It's a true statement. What does that mean? It means basically for example, I mean, it means basically like big divided by big is the same as, this y plus b. According to this right here, you're going to get the same slope. It's the rise over the run. Well, what is that? In this case, divide by x on each side, and you're going to get some m. And I'm claiming all of them do. Yeah, if that's going to be the case, that means this guy plus this guy has to equal some r times b over some r times a. And that will cancel. 1 over 1, that's b over a. There's some y over x, and it's equal to some, I don't know, some q times a, and the same q times b. And when you do them, forgive me, it's equal to something like this. So in other words, this would be, q times some b, q times some a, that's b over a. And yeah, I mean, it would work that way. If that's the case, you guys, if you can get things to look like that, this is very important. This is true. In other words, so there's similarity of triangles within a particular, the rise over the run associated with the big triangle is the same ratio as the rise over the run with the smaller triangle is the same ratio as the rise over the run for the smallest triangle. If that indeed, and it is, and we're going to show that that's the case, and that ratio is m. Now, if that's really what it is, so you could say big divided by big within the big triangle, big divided by, or whatever. I mean, rise divided by run for the big triangle is equal to rise divided by run for the smaller triangle is equal to rise divided by run for the smallest triangle. Yes. So what does that mean if you can actually say that? And let's actually prove that. It's not like, we're writing all this, we said all this. Certainly this will be if any rise over run is going to be equal to the formula, well, it pertains to this formula, divide by x on each side, m equals y over x. That m will be the case for all those, so they're all equal. Yeah, okay, great. So what? What are you trying to say? Well, what I'm trying to say is you could go here and you could say, okay, let's not worry about this one, the third thing. We established these two things are equal to each other, or we're about to establish that they're equal to each other. If you multiply by x on each side and also multiply by a on each side, you get ay equals bx. And then you could say, okay, let me take a and forgive me here. Let me take a and divided by x, or let me divide x by, let me divide each side of the equation right here. Let me divide by a on each side of the equation, and let me divide by b on each side of the equation. What just happened here? Let's just make sure it happened right. Okay, yeah, it did. You're essentially saying that one side of one of the right triangles divided by the corresponding side of another right triangle, that ratio, so associated with the rise, the two rises divided by each other in the appropriate way, is equal to the two runs divided by each other in the appropriate way. So y divided by b equals x divided by a. The two rises, the two different rises, because they're in two different triangles, the two rises divided by each other is a ratio which is equal to the two runs divided by each other. So on and so forth. So there's all kinds of, and you've seen this. I'm sure many people have seen this. There's all kinds of ratios that we can establish. And a lot of algebra that we can do to get us through what we want to be doing. How this all plays out. That's all great. That's all great if this is true. I'm going to play devil's advocate and say I don't know if it's true or not. It turns out it is. Turns out it is. When you go here, it's going to work. It's not an issue. It works. It's true. But let's see what we can say vis-a-vis this stuff. Okay, so it is. Is it true? I hope if it is true, everything I just said is true. Let me prove that it's true. Let's actually prove that that's actually working like that. Well, I got an idea here. Depends how far back you want to go and how rigorous you want to be on so much of this stuff, but I'm trying to be relatively rigorous and I'm trying to be very intuitive in our presentation here. So let's keep doing that and see what we can say. I'll tell you what I'm going to do. We're going to prove that the assumptions that I just made hypothetically are indeed true. So then we just say, hey, they're true, and then we're done, or at least largely done with a good part of what I wanted to discuss. Absolutely. We're done with a good part of the stuff that I want to discuss if we can prove that proposition that we made, that we supposed that y equals mx plus b and this whole thing, how these ratios work. I'll tell you what, we know something about areas. If you add two areas together, forgive me, time out. If you know, this is basically easier done than said, guys. Look at this big triangle. Why don't we find the area of that big right triangle? Well, I tell you what, there's a congruent right triangle. There's a congruent right triangle. There's a right triangle right here, big right triangle. I can make an identical big right triangle to this and put it up here and kind of glue them onto each other. In other words, if this is a big right triangle right here, let's say this is a scaled down version of the big right triangle over there. Here's the big right triangle, 90 theta, 90 minus theta, I get it. Why don't you draw another big right triangle that's opposite interior angles are congruent, that's theta, and this is 90 minus theta. They're not only similar triangles to one another, they are congruent triangles to one another. They've got, as we said, here's a 90-degree angle, here's this. This and this are congruent. That and that are congruent. Well, that and this are opening up 90 degrees. So that and this are opening up 90 degrees. That and this are opening up 90 degrees. By SAS, they're congruent triangles. What does that mean? The area of this triangle is equal to the area of that triangle. Well, what's the area of this triangle? Well, I mean, wait a minute. The area of this triangle equals the area of that triangle. So if I just find the total area composed of these two put together and divide by 2, I'll find the area of the triangle. Because this triangle plus that triangle, these are identical triangles. This area equals that area, and when you add them together, when you add these two areas together, these two areas together are equal to the area of the rectangle, and that's length times width. Divide by 2 on each side, or multiply by 1/2 on each side. Area equals 1/2 length times width. A lot of times they write it area equals 1/2 base times height, etc., etc. Let's get this straight. I think we got this. Let's take this real big triangle and find its area. How do we find the area of that really big triangle? You pretend that it's 1/2 of a big rectangle. A rectangle composed of two triangles, each one identical to this one. So those two identical triangles added together give you the entire area of the rectangle. So if you take half the area of the rectangle, you'll know what the area is of one of those big triangles. And that's what we did over here, guys. So I'll tell you what I'm going to do. I'm going to find the real big area. I'm going to use the formulas we already know. And we'll kind of take it from there. Tell you what I'm going to do. Look, total area, total area equals total area. I'll tell you what I'm going to do. 1/2 base, here's the base, a plus x. Here's the height. So here's the base. Here's the height. And that is the area. 1/2 base times the height is the area of the huge triangle. Now let's get the separate triangles together and figure out what's going on here. This triangle, so I'm just going to add all the pieces that make up the big triangle. I found the area of the big triangle. Hard to look at, but there it is. 1/2 base times 1/2 base times height, area of the big triangle. The area, and that area of the big triangle is the area of the big triangle is the sum of the areas, this area, and that area. All right. 1/2 AB. Let me see what we got here. Yeah, that's looking pretty good. So that's it's 1/2 AB. This guy right here is 1/2 XY. I did it a little differently last time, but that's okay. This is X. This is X. That's B. And that is a rectangle composed of two identical right triangles. What's the area of the right triangle that is in there? Identical to the other right triangle that is in there, and they both compose the entire rectangle. What's the area of one of those right triangles? It's 1/2 base times height. It's 1/2 X times B. Yeah, but I want the whole thing. I want both of them. 1/2 X times B times 1/2 X times B plus 1/2 X times B is just X times B, or B times X. Doesn't really matter. Base times height is the whole rectangular area, and that's everybody. Okay. Tell you what, let's try to simplify it, I guess. Multiply by 2 on each side. Multiply by 2 on each side all the way across. Okay. True. See how this whole thing plays out. Let's go. Let's see what we got. Do the FOIL method right here. Take the A and distribute it across the Y and the B. AY plus A. So you got AY plus AB. Take the X and distribute it. XY. Let's see what we got here, guys. Right. XY, XB, or BX. And let's see what we got here. Set equal to this, which is AB plus XY plus 2BX. Yeah, okay. let's start, let's talk a little bit. I mean, let's see where we're going to go with this thing. Let me subtract AB on each side. Let me subtract XY on each side. And then I got AY plus BX equals 2BX. Really? Yeah. Number of ways to go. Subtract, BX is the same as 1BX. Subtract 1BX on each side, you got BX. Yeah. That has to be the case if the sum of the small areas equal the gigantic area which they compose. The sum of all the small areas is indeed the major large area there. The major large area, we found an expression to describe it for the major large area. The major large area was this, 1/2 times this. Then I added the parts together. The small parts added together equal the entire area. The entire area can be expressed this way as well. And the entire area can be expressed this way as well. If you're going to add the small pieces, that'll give you the entire area. Multiply by 2 on each side, you get down to here. What's going on here? Let's play this a bunch of ways if you want. Why don't you divide by A on each side? I almost got a better idea here. Let me kind of think. Let me divide by A on each side, and let me divide by X on each side. Let me divide by A on each side. Let me divide by A on each side. Wait a minute, that's the slope. That's that slope we said it was earlier. We said y equals mx plus b. It didn't matter which one it was. Y equals mx plus b. M happened to be the rise over the run. M happened to be the rise over the run. B over A. Notice that A and B are not really specific. Neither are X and Y. We simply know that if you take this ratio and multiply it by X, you will get the Y. That's indicative of this thing behaving as though it's a straight line, and the y equals mx plus b lies on the triangle, lies on every similar right triangle that is encased in here. And that's not, to me, that doesn't mean I'm right. To me, that's never been obvious. Yeah, I know we can graph stuff and see how, yeah, it sure looks like a straight line, doesn't it? But we actually proved that, you know what, for any A, for any B, B divided by A, if you multiply it by a different X, you're going to get a different rise. You're going to, if you take a rise of B, any rise of B on a right triangle, and any rise of B associated with a run of A, for any right triangle that is similar to another right triangle, no matter how big that one may be, if you multiply it by the run that one's making, you'll be able to get y. And that's really indicative of y equals mx plus b. The slope indeed is this. That guy right there is the slope. Yeah, there's something a little bit bigger here. I don't know if it's bigger, but it's actually the same thing, just spoken a little bit differently. Divide by x on each side. Divide by x on each side, you got y over x equals b over a. B over a equals y over x. For all right triangles that are similar to, for any two right triangles that are similar to one another, for any two right triangles that are similar to one another, the rise divided by the run for one of those triangles, big or small, is equal to the rise divided by the run for the other right triangle, no matter how big or small it is. If two right triangles are similar to one another, they have the same slope. The rise over the run equals the rise over the run. Does not matter how big or how small Either one of them is. One could be a very, very huge triangle compared to another, and it won't matter. Or they could be very close in size. It doesn't matter. The rise over the run is equal. What also is interesting about this is, we kind of discussed it already, you could say, well, Jim, could you have done something else? Well, yeah, I could have. I could have divided by A on each side and divided by B on each side. So I could have done it a little differently. I divided by A on each side, then I divided by X on each side, but I'm not going to do that. I'm going to divide by A. I'm going to take this equation right here, and I'm going to divide by A on each side, so y equals B over A. I'm going to divide by A on each side, so y equals B over A times X. Then I'm going to divide by B on each side, Then I end up getting y over B. Well, that's just 1 over A is left over. 1 over A times X over 1 is X over A. Now, what's going on here? Here I am comparing the rise of one compared to the rise of the other, y divided by b, and that's equal to the, call this one the big one, that one the small one. Maybe it makes it easier to kind of like keep track. The big rise divided by the small rise is equal to the big run divided by the small run. This is stuff we were talking about earlier. All that stuff is verified. Look how we did it. We verified it looking at areas. And that plays a bit of a role. We want to do something like that. So there's some neat stuff that goes on there. Now, really kind of out of the picture here in this whole discussion, kind of a glaring situation that's out of the picture in this whole discussion is it's kind of out there. It's like, well, wait a minute, isn't this right here? Isn't that a hypotenuse? Isn't that another hypotenuse? This is a small hypotenuse. This is a big hypotenuse. And this is the very biggest hypotenuse of them all of these three. Nobody's talked about the hypotenuse. Well, the ratio, let's just, it will show this. The ratio, sides, the ratio of sides within a triangle are equal to the ratio of sides in the other triangle, provided that they're corresponding to one another. The rise divided by the run is equal to the rise divided by the run is equal to the rise divided by that entire run. Absolutely. We never really specified what A and B were, nor what X and Y were. If that's the case, what I proved for B over A equals Y over X, that holds for everything. I never specified what the angles were, what the sides were, or anything. Y plus B divided by A plus X, the quantity Y plus B divided by the quantity A plus X is the same as the quantity Y divided by the quantity X is the same as the quantity B divided by the quantity A. That's pretty neat. That absolutely true. Is it like that with, and we also said other stuff. We said the large rise divided by the small rise, the large rise divided by the small rise is a ratio equal to the ratio of, so the ratio of the large rise divided by the small rise is equal to the ratio of the long run divided by the short run. And not only that, those two are equal to the hypotenuse, the long hypotenuse, not the longest hypotenuse, but the long hypotenuse divided by, associated with this guy, divided by the short hypotenuse. Long hypotenuse divided by short hypotenuse is the same as the ratio of, big rise divided by small rise. Big rise divided by small rise is equal to big run divided by small run is equal to big hypotenuse divided by small hypotenuse. But we proved all of that except for the hypotenuse business. To do that, we got to figure out a formula for the hypotenuse. And there's some neat formulas out there that go into it. So you can kind of debate how you want to go about it. But this is of interest. Let's see here. Let me show you that third thing is equal to the other two. We said big rise divided by small, big rise divided, two different triangles. For the two different triangles, let's call one of them triangle S for small triangle, and the other one triangle B for big triangle. And they're similar, same degree measurements, their 90-degree angle is present in each one of those right triangles. They're similar to one another. And we said that, associated with the long rise, associated with the big rise, and associated with the small rise, big rise divided by small rise, big rise divided by small rise is equal to big run divided by small run is equal to big hypotenuse divided by small hypotenuse. The ratio of big rise over small rise is equal to the ratio of big run over small run is equal to the ratio of big hypotenuse to small hypotenuse. That last thing we haven't proved, but we're going to. How does that work? Well, remember I told you you can always break up triangles, any triangles, into two right triangles, and maybe that makes our math a little bit easier. So let's see how that works out. Give you a couple looks at this. I saw what I bet is a very famous proof of the Pythagorean Theorem. There's many proofs of it, apparently. I'm going to give you two of those proofs, actually, is what my goal is. This one proof I'm going to give I saw in a book some time ago. Excellent proof. I bet you it's somewhat on the famous side, I guess you could say. We'll take a look at it. All right, guys. Here's one way they prove the Pythagorean theorem. They take, wish I had, actually I do, actually using the ruler might even make it not as easy to look at. I don't know, let's see, hopefully I can draw this halfway decently. Let me draw a big square. I don't know how good I drew it, but it somewhat mimics a big square. All right. Let's draw that is horrible. All right. Maybe I do need to get better at it, guys. Hold on. Let me try to. I'm going to do a square within a square, I guess, kind of thing. Let me just see if I can pull it off. Try this without. Guys, I don't know. These ruler might mess me up more. I told you that in the beginning. It might mess me up a little more than it's going to help me. Let me just go with it. Let me kind of look at it. I mean, I already don't like the way it looks, to be honest with you, but let's just keep going with it. All right, let's see if we can do this. Um, this might be a little bit better. Make an alteration there, guys, to make it work, I guess. This is of length A. That's of length A. That's of length B. This is length B. That's length A. That's length B. That's length A. That's length B. That's length A. This is C. This is C. This is C. This is C. Maybe it looks familiar. That's a square within a square. Guys, from side angle side, side angle side, from side angle side, that side angle side, side angle side, side angle side, side angle side. All four of those triangles on the outside are congruent to one another. They have the same area. The square on the inside has an area of length times width, which is C times C. Cross every bridge we have to. The square on the outside has length. The square on the outside has whatever you want to call length, whatever you want to call width. The square on the outside has length A plus B and width A plus B. So this length right here on the outside, perpendicular to this length right here, they're two equal lengths. The length of the width, let's call this the width, the length of the width is A plus B. The length of the length is A plus B. The area is the quantity A plus B times the quantity A plus B. It's, whatever you want to call length, whatever you want to call width, guys, doesn't matter. They're equal length here, but what's the area of the square? The area of a square is the side squared. Well, here's the side, A plus B, the quantity A plus B squared. The area of the whole entire figure is the area of this great big square, which is length A plus B times width A plus B. And each one of these, 1, 2, 3, 4, there are 4 triangles, each one with area A plus B. And there's a relatively big square, smaller than the square on the outside. Do the FOIL method here. Four times a half AB is 2AB. C squared is C squared. Subtract 2AB on each side. Not my proof. I saw it a very, very long time ago. The beauty and simplicity of this proof is quite remarkable. So that's pretty fascinating. That's just amazing. It's just amazing. I'm going to show you another way to look at it in a second, but let's kind of, as they say, first things first. Let's we know this. Now, I said some things earlier. Can we draw some conclusions here? Well, we said a bunch of things. We said things about right triangles. And I'm telling you, you can extend it to every kind of right triangle. And the way you want to do that is, you'd say, okay, well, look, we were able to prove this, that beautiful result that gets used everywhere, gets used in a lot of places. C squared equals A squared plus B squared. Let's talk a little bit. Let me, you could play this a whole bunch of ways. Let me take two identical you could the kind of triangles you could put. Let me just say here. I almost want to embed them. I almost don't. Let's just see here. These are similar triangles. This guy's got a theta right here. Enough said, and that's a 90-degree angle. This is, how do you want to go with this? How do you want to do it? Let's take a look at this guy, and let's say this is A, this is B, this is C. And now I know I can really say something about C. If I really want to, we know how this plays out. I mean, if you do the square root of both sides, you're talking about this. Absolutely you are. Let's look at the other one. I'll tell you what I'm going to do. Let's call this guy, what do you want to call him? Let's call him X. That's the hypotenuse. We'll call him X. We'll call this guy A. We'll call this guy B. And these are similar triangles. Now, I don't have too many comments right now about the X and the C. I can tell you the X, just looking at it, I can tell you the X is going to be longer than the C. I get all that. You do remember some conclusions that we've drawn. We've said a lot of things. We said that corresponding sides, if I took big B and divided it by small b, that's the same. That was the rise over remember the rise over the run? Yeah, and I also said the rise over the run. I know I said that. Yeah, we said a whole bunch of equations. We said everything equal, in three particular manners. Rise over the run. But we also went across the triangles and said, okay, rise over rise. Big rise over small rise equals big run over small run equals big hypotenuse over small hypotenuse. Well, that last thing I never said, but now I'm about to say it. We did say this, though. Big rise over small rise equals big run over small run. And yeah, I'd love to be able to see, I'd love to be able to say, I don't know how to make one smaller than the other here. I'd make this a giant C, which is equal to X, I guess. Giant C divided by small c, which is the same as, we just said it's going to be X. So whatever. Sometimes it's not that obvious what the small letter is and what's not when you're talking about the C's, right? I'll tell you what I'm going to do. Well, I will tell you what I'm going to do. I mean, it's equal to that, and that's equal to X over C. I'm going to say it's equal to X over C. Well, I'd like to show that. I'd like to prove that. That's a big C here. Let me get rid of it for now, but you got it kind of in the back of your mind. We did say this. Could I say that ratio? I could go the other way with the ratios, guys. You understand that any two ratios that are equal to each other, any two non-zero ratios that are equal to each other, their reciprocals are equal to each other as well. If two things are equal to each other and they're not equal to zero, then their reciprocals are equal to each other. I could just as easily have flipped this upside down and gone like this. Any two non-zero ratios that are equal to each other means that their reciprocals are equal to each other. Okay, we know that. Let me put it all right. So I don't care if you went small b over big B, small a over big A. If two ratios are equal to each other and they're not equal to zero, their reciprocals are equal. Doesn't matter. So it's not a problem. I'm going to say R. R is probably it's a positive number bigger than 1. Look at it. Just looking at it, we'll say intuitively that's the case. Yeah, I know. I'm hoping I can draw the conclusion that X over C is also equal to R. I mean, we're saying these guys are equal to R, but can we get it to here? can we get r equals x over c if r equals each of these? Tell you what I'm going to do. This is r times small b. This is r times small a. Is that true? Yeah, we look at it. B over b equals r, multiplied by b on each side, multiplied by small b, that's rb. A over a equals small r, multiplied by small a on each side. If I'm giving you this, get rid of him and go big B over small b equals r, multiplied by small b on each side. You get big B equals r times small b. Get rid of this, multiply by a on each side. That's all. You're doing this, guys. You're just doing this. Okay, so this, we know that's true. You know where I'm going. I hope I can say that x, which is equal to capital C, is going to be equal to r times small c. Everybody else, this guy's r times bigger than the corresponding part in the other triangle. This guy's also r times bigger than the other corresponding part. You know, what corresponds to this guy, small b? Multiply by this r, you get big B. What corresponds to this guy, small a? Multiply by this r, you get the big A. So the ratios are what they are. Big B is r times bigger than small b. Big A is r times bigger than small a. So big B is r times bigger than small b. Big A is r times bigger than small a. And big C is r times bigger than small c. If you want, call it x. Maybe it's a little easier to look at. I hope it's the case. We're going to prove it's the case. If x equals r times small c, you're done. Let's see what we got here. So what are we going to do here? See what happens. I'm hoping I'm getting that. We're hoping we're getting that answer. That it's going to be this. It was happening that way for him and for him. You saw it here. And you saw it here. Is it going to happen here? Yeah, I got an idea. Call this like the new A. Call that the new A, the new B, the new C. Let's see what happens here. Look, let's get something very, very straight, actually. Just to play it really safe. Now, I know I erased it. We know that the C right here, you guys, is the square root of the quantity a squared plus b squared. What is that? Heck, I don't know, I do know that it's, C equals the square root of C equals the square root of the sum a squared plus b squared, small c. Make that a little smaller. I don't know, guys. Forgive the over meticulousness here on some of this stuff, but just in case. It's a small c. Small c equals the square root of a squared plus b. Small c equals the square root of the sum a squared plus b squared. Okay. What's this guy equal to? Well, play the game. General format is this. Now just put everyone in their roles, right? I mean, we go to here, we get this. Let's deal with it. X is the new C. RA is the new A. The whole thing is being squared. RB is the new B. r squared a squared, r squared b squared, pull r squared out of there. Okay, sounds good to me. Square root both sides. The square root of a product is the product of the individual roots. The square root of a product is the product of the individual roots. The square root of a product is the square root. The square root of the product is the square root of the individual roots. The square root of r squared is just r. That's hugely significant. That's hugely significant because x over c is indeed r. Remember what we said, guys. The small c was equal to the square root of a squared plus b squared. X over c is equal to r times the quantity, the square root of the sum this and this are the same. Wow. Go somewhere, guys. I'm a little afraid that it won't be there. Okay. So you got yeah, you got it. You got it. Big B over small b equals big A. Big B over small b equals big A over small a equals big C over small c, which is the same as x over c, and all of them are equal to r. Every single side of any triangle, well, let's go for a little further. Every single side of any right triangle, every single side of any right triangle is proportional to a similar triangle to it. Any of the, stuff's easier done than say. I think you guys know where I'm trying to go here. You do any kind of ratios you want to do here. In fact, kind of interesting. Let me do it, and let me try to say it again, I guess. That's RC. What is RB? What is RB divided by RC? What is the, here's the angle theta. I think you might know where I'm going here. What is RB divided by RC? RB divided by RC is B over C. That's the same as B over C right here. What is RB divided by RA? It's the same as B over A. Because RB divided by RC, the R's cancel. RB divided by RA, the R's cancel. RB divided by RC, RB divided by RC, RB divided by RC is B over C. RB divided by RA, the R's cancel, that's the same as B over A. RA divided by RC is A over C, it's the same as this. The sine, the tangent, and the cosine is identical when you have a right triangle with particular measurements associated with the acute angles that are in there. In plain English, if you got a right triangle and there's a particular theta that's we're not talking about the 90-degree angle. There's a right triangle and one of the acute angles is theta. If you can find another right triangle that has an angle theta in it, that's not the 90-degree angle, just like the other one was not the 90-degree angle. A 90-degree angle and an angle theta in it, and find some other triangle that has the same phenomenon going on. no matter how huge or how tiny the other triangle is compared to the other one, the ratios for sine, cosine, and tangent are identical. The ratios under consideration are identical, and within the triangle, and then outside of the triangle, you could say, well, what is long rise, RB, divided by short rise? RB divided by B is R. What is long, RB divided by B is R. So long rise divided by short rise, RB divided by B is R. Long run divided by short run, RA divided by A is also R. Long hypotenuse divided by short hypotenuse, RC divided by C is R. The ratio, if you're comparing appropriate sides, corresponding sides, all the ratios that we talked about are for real. For all three sides of any right triangle, including the hypotenuse. Can we extend this to any triangle? Yes. Let me do that really quickly. What do you want to say about this? Well, let's say you got all the angles and they're identical between two places. So let's say I'm trying to make this not look like all right, let's say those are similar triangles. What do you mean by similar triangles? Well, the criteria that we've done so far with triangles that have a 90-degree angle in them, triangles that are right triangles, the criteria for the right triangles to be similar triangles, where it always worked, quote unquote always worked, the criteria that we always looked for was there are two right triangles and there's two right triangles, and so two right triangles, they both have 90-degree angles in them by definition, and the other two angles in either triangle are congruent to the other two angles in the other triangle. They all have the exact same angular measurements. They all add up to 180 degrees, but we know that happens with any kind of triangle. These all add up to 180 degrees. But we know that for two right triangles, if they are the exact same angles in each one, even though the sizes of them are different, if the angles are exactly the same, they're similar triangles. And we're saying, does that work? Well, I could say to you, yeah, I think I can say that to you, because if I drop a perpendicular here, and I drop, and again, this is not a good drawing, guys, but let's assume it's the more I look at it, the less good of a drawing it is, actually. But let me, a little bit better. That's not much better, but okay, it's a little bit better. All right. If this is alpha, and this is alpha, and this is beta, and this is beta, that's a 90-degree angle. And that's also a 90-degree angle right here. Okay, we know that. This guy right here is going to be, we can play this, we can play this a bunch of ways actually, but let's just play it. This guy right here is going to be There's about no good way I can write this. I guess I want to leave myself a lot of room, guys. Let's see what we got here. Let's call this guy 90 minus alpha. Yeah, it makes sense. It's got to be. Let's call this guy right here 90 minus beta. Yeah, it's got to be that too. I don't need to prove to you guys. Well, I do, and it should be pretty quick. If this is 90, this is also, this is not made up. It's also 90 minus alpha. It's identical to this. And this is 90 minus beta of the second right triangle there. Wait a minute, they all measure right, and not only that, you broke them into that triangle and that triangle are similar to each other. That triangle and that triangle are similar to each other. What the heck does that mean? That means if this guy right here is, I don't know, if this guy right here is A in length, and this guy right here is B in length, I know what you're thinking. Yeah, those sure look like hypotenuses. Yeah, they sure do. Let me try to think here, guys. And this right here, just try to say here, guys, something. If that's the length under consideration, this, yeah, let's go that way. Let's go. We know this and this are similar triangles. This and this are similar triangles. We already know the hypotenuse game. This is r times bigger. This is RA. This is RB. Okay, what does that mean? Well, RA divided by A is R. RB divided by B is R. So RA divided by A is R. RB divided by B is R. Gee, I don't know. You broke it up, huh? You're going to have to say then that for this guy, there was a length here. And I'll tell you what, I mean, the length of this guy, you know, when you break it, let me just try to think here, guys. I just want to talk to you in a way that's going to make some sense. They give you something like that. Let me just see here, guys. Let me just kind of talk about it. Just want to argue this a little bit with myself. That's that. That's that. We're making that claim. So if they're similar, because just the way I broke these up, this is all believable. This, man, I tell you, I don't know what this thing was. I mean, I'll say this length right here, right there, that was X. This is why I know it's something. You know, let's say the C, we'll call that a small, we'll call that the whole long thing, we'll call it small c, is X plus Y. Well, if that's the case, if that's X, we said that it's got to be R times B. We said the proportions are all there. This is Rx right here. This is Ry right there. I'll call that guy, you know, what do you want to call this one? I mean, I guess we can call it big C, right? We'll say big C was Rx plus Ry, which is equal to, pull an R out of there, X plus Y. Wait a minute. Big C over small c is R times the quantity X plus Y over the quantity X plus Y. we could call this, this guy big A, big B. Yeah, I mean, big A over small a is RA over A, that's R. Big B over, so big A over small a is RA over A, which is R. Big B over small b is RB over B, which is R. Big C over small c is, well, it's kind of interesting. It's R times the quantity x plus y over the quantity x plus y. And this is, it's going to be R times the quantity x plus y over the quantity x plus y. Still an R. So you could have done it like that too when you're doing that. And again, you could extend this in a myriad of ways. It's coming out to this. That's out of there. That's just R, whatever that R happened to be. And everything else works too. Some R there. Everything else works too. I mean, you can go, what's B divided by A? It's the same as RB divided by RA. That's still B over A. That's the same as R times the quantity x plus y divided by the quantity x plus y. No, hold on. Time out. Let me think here. Okay, you didn't have to. That's a different phenomenon. Let me try it again. If you go B divided by A, that's the same as RB divided by RA. Absolutely. If you go the real long one divided by, the real long one divided by RB, that is R times the quantity, the real long one, which is R times the quantity x plus y divided by RB. Well, R times the quantity x plus y divided by RB is just x plus y over B. The R's cancel. Well, wait a minute. This whole big thing, R times the quantity x plus y divided by RB, is the quantity x plus y over B. That's the quantity x plus y over B here as well. So all these correspondences hold when you want to do something like that. It really freed us up when we were able to prove the Pythagorean theorem. Now let's look at the Pythagorean theorem in just one more way, and that should be about it for the discussion on this. So let's see what we could say here. It should go pretty straightforward. That classic one that I show, I'm calling it classic because it must be a classic. It's just so straightforward, you guys, that it was done, and not done by me originally. Who knows when they had actually proven that? And there's definitely other proofs to the Pythagorean theorem. I'm going to give you another one based on what we know. We'll take it from there. All right, guys. We try to think of a way we could maybe do something else here. Let's take a right triangle. Maybe just stay with. I shouldn't get too fancy here, guys. I want to make it a little less symmetric to kind of give it more of a general feel to it, because everything we're solving here has got a more general feel to it. Let's try it again. That's a 90-degree angle. Um, and just going a little bit on memory here, guys, and some of the stuff I was thinking about how to do it. There is that's length A, that's length B, and that's the hypotenuse, length C. If you drop, now let's talk again. It's that ever-present, there's a 90-degree angle present. There's a 90-degree angle present, and there's a theta present. That means this guy right here is going to be 90 minus theta. If you drop a perpendicular altitude right here and call that height z, if this is theta and that's 90, that's 90 minus theta. This is 90 minus theta, and that's 90. This right here is theta. What are you talking about? I'm talking about 90 degrees, I'm talking about 90 degrees, 90 minus theta, and theta. I'm talking about 90 degrees. So I said 90 degrees, 90 minus theta, and theta. I said 90 degrees, 90 minus theta, and theta. And I also said 90 degrees and 90 minus theta and theta. All three triangles are similar triangles. Now, I'm starting this proof as though I haven't proven the Pythagorean theorem. We've proven it with the help of some brilliant people who have proven it before us, and we had it proved. We were able to prove it, and we were able to get a good answer. We were able to do that, but now I'm going to pretend I haven't done it. Once I do so, all the conclusions that I drew earlier for similarity of triangles that we just drew, just now, in this same video, all those conclusions that we drew regarding similarity of triangles, because we did prove the Pythagorean theorem with some work that people had shown us from the past, from I don't know how long ago, but some brilliant work that people had done, that other people had certainly done and shown us. Because we were able to prove the Pythagorean theorem, we were able to finish all the conclusions that we wanted to finish. Absolutely. Now let's pretend we haven't done that yet. Let's prove it here, and then we know, hey, you know what? Go back. We already know what the conclusions are. It's c squared equals a squared plus b squared, and the similarity that goes on, how the hypotenuse has the same similarity aspects as all the legs have. We proved that already when we looked at an earlier proof of the Pythagorean theorem. So we know that will hold. All of what we said indeed holds, so we don't have to do it again, as long as we prove it here. Let's just pretend we hadn't done it, but if we can prove the Pythagorean theorem right now, as though we hadn't done it, we could take that conclusion and use it exactly the same way that we used the earlier conclusion, and we prove everything where we prove. So everything holds if we can show this again. You know, we've already proven it. We've already looked at it. So let me get some more chalk here, guys. All right, so what can you say? I'll try to make it easy. This looks familiar. Again, I think I've made the point, but just for everything that we've proven is correct, period, and we're done. We're actually done. Even if we didn't do this, what we wanted to show, we showed it, and we're done. Everything we wanted to prove is proven because we were able to look at some brilliant proofs. We were able to look at one brilliant proof that someone else had done that was excellent, and we talked about the Pythagorean Theorem. Prove the Pythagorean Theorem here, and it's the same exact proof, and everything we said, of course, holds. It's not going to change. The theorem is the theorem. We can show it in a different way, but it's not the theorem is not going to change because we had done it rigorously, we had done it correctly. We're going to do it again and just kind of verify that. And then everything that we had said holds for us, and that's important. I'll tell you what. A lot of ways to go here. I'm just trying to think of a good way to go, I guess. We could say this. I mean, there's a side here that the whole thing is C. We could call this side right here X. And we'll call this side right here C minus X. So right here, that's X. That's that. What do you think? Okay, well, here's what I think. Number of ways to go here. Let's just take these two perpendicular corners to one another. This side and that side are perpendicular to each other. 1/2 A times B is the area, and that ends the story. 1/2 A times B is the area of the whole triangle. Composed of 3 triangles. Well, composed of 2 triangles. You cut it into a small triangle and a not so small triangle. You put them together, and you got one big triangle. And they're all similar to each other. That's important. So take A, take B, go A times B times 1/2. This one right here is X times Z. Let's see what we can say here. I guess there's a number of ways to go here. You can also say, here's the height Z, and here's the long length C. 1/2 Z times C. Here's Z, here's C. It's another way that it's certainly true. Both are true. Just trying to remember, guys, I'd done this a little, again, each one of these I'd done differently when I'd first done it. So let's see what we can do here. Try to think here. So we're looking at it, and a good way to look at it, I guess. We could say that you could also go Z, the quantity Z times X, 1/2. The quantity Z times the quantity C minus X would also get us there. So what are we talking about? All these are true. Let me just kind of, I'm not exactly thrilled with the entire argument, guys, but 1/2 Z, 1/2 ZX plus 1/2 Z C minus X. Actually, and that's true because if you distribute this throughout, you get 1/2 ZC minus 1/2 ZX plus 1/2 ZX is 1/2 ZC, and that's this. True, you know. This and this are definitely true. Let me see, is there any way we can kind of get an idea where we want to go with this? The way I had kind of looked at it is a lot of ways you could go here. Let me think. can look at it and say, okay, well, z is whatever it is. Can we figure out, how to kind of try to bring this thing in here, kind of have c in there in some way. So there's nothing wrong with this. The argument's okay, but as we look at it, we're trying to actually there's just a lot of stuff that's true, guys. You can go like this. You can go long leg. There's a whole lot you can say here, guys. Let's just kind of throw it out there, I guess you could say. The way it's kind of set up is whatever's opposite the 90 minus theta over whatever's opposite the theta. So go whatever's opposite the 90 minus theta over whatever's opposite the theta. Whatever's opposite the 90 minus theta over what's opposite the theta. So that's z over x. So let me just kind of, let's play that game a little bit. And here, whatever's opposite the 90 minus theta, whatever's opposite the theta, and that's whatever's opposite the c minus x. Okay, guys, so I'm going whatever's opposite the 90 minus theta over whatever's opposite the theta, whatever opposite the 90 minus theta over whatever's opposite the theta, keep going, and then whatever's opposite this guy for this triangle, whatever's opposite the 90 minus theta over whatever's opposite the theta, and that's z. True. So we see here, I've got a lot of data up here. How much of it do I actually need? We'll see. We can prune things as we need to. Is it true? There's a lot of ways to go here. C minus x. So I tell you what I'm going to do. I'm going to say, guys, look. I mean, there's a number of ways to go. Let me try to not. Let me do a couple things here. Let me try to find the area of this triangle, then the area of that triangle, and then add the two triangles together. I got a lot of data here. How much of it do I need? I'm going to need some of it, maybe not all of it, but let me think here. So it's easier when I was thinking about it, a little more casual setting, I guess you could say. Let's just see what I can say, guys. I am going to say basically that the area of the entire place, I mean, this A right here, this is what A is equal to. So we got that. We can also say that A is equal to the sum of 1/2 xz. Okay, I got 1/2 xz. Okay, I already got that. I already got all that. So let me write that in a separate way then maybe. What I would do is, you could say a whole bunch of things. You can go right here and multiply by, just for these two right here, multiply by x on each side. Z equals B over A. And notice what I'm doing. I'm not really comparing hypotenuses. I'm not sure how right now I'm pretending I don't know what the hypotenuse, I'm pretending I don't know how the hypotenuse relates to other hypotenuse that's present, even though they're similar triangles. We already know that from the past proof when we proved what c squared was. C squared equals a squared plus b squared. C equals the square root of the sum, a squared plus b squared. C equals the square root of the sum, a squared plus b squared. But if I don't know that, I'm going to work just with, I'm going to work without really looking at the hypotenuse per se. I mean, look, man, the B is a hypotenuse related to this triangle. The A is a hypotenuse related to this triangle. I get it. And the C is a hypotenuse related to the big thing. I get all that. But before I was able to prove, and I'm now and we're good. Nothing was wrong with what we've done. Everything was done right, correctly. But now we're going to say we're going to pretend we don't know that relationship of how the hypotenuse relates to another hypotenuse. Well, it relates the same way that, the big rise divided by the small rise is equal to the big rise divided by the small rise is equal to the big run divided by the small run is equal to the big hypotenuse divided by the small hypotenuse. We know that from past work, but now we only know about the big rise divided by the small rise being equal to the big run divided by the small run. That's all we're going to say we know. We're not going to talk about the hypotenuse yet. And once we do, all the other conclusions fall into place. That's what I've been trying to say, I guess. So you look at this, and you say that Z is B over A is this opposite this guy, right? Right, absolutely. Is B over A, this ratio, is the same as Z over X. So times X. Okay. Sounds good. Sounds good like that. And C, C minus X. So let's just see here. That's equal to that. That's Z. Just see, guys, real quick here. How the altitude Z is the ratio B over A times this. Yeah, because B over A compares to Z over X. So B over A compares to Z over X means that Z is B over A times X. Good enough. The other one is saying that C over X is opposite this guy, right? C over X over Z is equal to B over A. So C minus X over Z is equal to C over X over Z is equal to B over A. So that's equal to B over A times Z. Tempting stuff here, guys, to look at it. You can see how it all works out. You got this guy with X, and just try to see here, guys, where we want to go with this. That's with Z. Trying to think here how I put the X in there. Yeah, I think I got this, guys. I mean, we can go a couple ways here. Why don't you solve for X? You can see where I'm going in a second. Multiply by A over B on each side. Multiply by A over B. Multiply by A over B on each side. And you got A over B times Z. Now you're probably wondering, okay, what's going on here? Well, that's X. That's X in terms of Z. And that's the other part of the long hypotenuse. The whole thing is C long. This whole thing is C long, guys, where I am right now. Here to here is C long. This is C minus X. That's C. C minus X, C, the whole thing is C long. Z times C will be the same as, we said this. How much of that do we need? We'll cross every bridge as we need to do it. I think the way you want to go here is you don't want to use, I don't want to chase my tail too much, guys. I mean, this is all true that's all true. I'm kind of leaning in different directions here. Why don't you take x plus c minus x and add them together? So the way I'm looking at it is, if you really want to do that, if you want that to be the case, you want one half z. Z is the altitude. And z is the altitude. And what is c equal to? C is equal to x plus c minus x. Yeah, I know, we've already talked about that. Well, yeah, let's keep talking about it. This is that. What is x? X equals a over b times z. Got it. And c minus x equals b over a. X equals a over b times z. It makes sense. I mean, it makes sense. X is, the short rise over a long run. So you know what I mean? You could say, okay, short rise over long run, short rise over long run. A over b equals x over z. X equals a over b times z. C over z is the long run, is the long rise over the short run. And that's the same as long rise. So that's b over a. That's not, that's b over a is equal to that. So b over a times z, b over a times z is going to equal. Let me see here. Yeah, right. Exactly. So b over a, so that's long run, long rise over short run, long rise over short run. B over a times z will give you that. Okay, so you got that. That's pretty big. That's very important stuff. What happens is you pull the z out of there. You pull the z out of there, and you got 1/2 z squared AB plus BA. Okay, so we got all of this. Let's kind of take our time getting there, guys, but you got it to here. That's area. And let me just try to think about it. Yeah, Z. Absolutely, you got that. And okay, we got this for the area, guys. It came from there. And that's equal to AB. So what we got is, I'm just trying to, there's a couple arguments you can make here. Once you got it to there, you can actually yeah, okay, this is going to be great, guys. It's going to be, we put this guy down early on and we sort of left him alone. He's not going to be left alone for too long. And this is also true. I mean, all the data is there, guys. And to a large extent, it's very useful to us. All of it is. What's going on here? What's this? This is the area, guys, still. I mean, let's just stay with it. 1/2 z squared, and here we go. Let's get a common denominator, guys. Let's have AB as the common denominator on the bottom and see what happens. AB is the common, let's get AB as the common denominator on the bottom. What does that mean? Multiply A and B together, and you got AB. Let's get a special one here, so I have AB as the common denominator, A times B, common denominator. Special one is A over A. That's special one is A over A times A over B. That's A squared over AB. Special one here is B over B. That's B squared over AB. B over B, that's B squared over AB. Starting to look like something. And that's the area. Okay, let's take a look at that. Very important. What to erase, what not to erase, I guess. Well, we'll erase a lot. This is pretty important because a lot of ways to go, and I just want to argue a little bit with myself. Let's look at this. 1/2 AB equals all that. Well, A equals A. Forgive me, guys. Let me just check my. Yeah, mic's working okay. All right. A equals A. 1/2 AB. And I'm not using any similarity associated with the hypotenuse. I don't want to do it. I'll use the similarities I can use. I can use all kinds of rise over run or run over rise, or I can call whatever I want the rise, and I can call whatever I want the run, as long as I'm consistent and I'm talking about the legs. And that's all I've been doing. I haven't talked about, I broke up the hypotenuse and made legs out of it, and then when I add them together, I get the whole thing. 1/2 z squared a squared plus b squared. Let's multiply by 2 on each side. Tell you what we're going to do. Let's divide by 1/2 on each side, which is dividing by 1/2 on each side is the same as multiplying by 2 on each side. Multiply by 2 on each side, and then multiply by AB on each side. And you end up getting AB squared equals z squared a squared plus b squared. Yeah, that's pretty interesting. What's going on here? Well, the way you can kind of look at it is, some of this stuff is easier done than said, I guess you could say. You could get the square root of both sides. Now, what are we doing here? This is, if you get the square root of both sides. They're all positive numbers. Yeah, that a squared plus b squared is really, 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 really standing there, huh? Do you see it? Look carefully. Multiply by 1/2 on each side. Why'd you even divide in the first place, you might ask? That's a good question, I guess. But multiply by 1/2 on each side. Isn't that the area? Isn't that 1/2 ZC? Isn't that 1/2 ZC? Look carefully. Bingo. We got it. One half ZC. Here's the big one, Z. See, if you take another triangle identical to this triangle and place it in a certain way, it's going to be a parallelogram. It's going to be a parallelogram, not necessarily a rectangle, not necessarily a square. Square is a special kind of rectangle, not necessarily a rectangle where there's 90 degrees on, at the corners, at all the corners. This won't, the way it is now, it's not going to be 90 degrees at the corners. That's for sure. It's not going to be 90 degrees at the corners. I'd have to build another one just like this, and and then turn it this way, turn it in such a way that I would have. Let me see what I actually would have. I mean, you put it like this, and the other one would be just like that. So where would it be? You'd have the B that way. You'd have part of it here, and you'd have the A over here. You'd have like an A over here. You'd have an A over here, an A over here. The B would be here, and then the C would be that way. That would be C. This would be B. That would be C, and this would be A. And then the area of the parallelogram would be 1/2 base times the height. What is that? Well, the base is C, the height is Z. The area of the parallelogram is base times height. It's Z times C. But if you multiply by half, you're finding the area of this. And that's the 1/2 ZC that we're talking about. 1/2 ZC equals 1/2 Z what? You're stuck. It can't be something. It has to be unique, guys. 1/2 Z. Congratulations. Here we are. Multiply by 2 on each side, divide by Z on each, multiply by 2 on each side, and then divide by Z on each side. We did that without assuming similarity of the hypotenuses. I don't know if that's the right way to say the plural of hypotenuse, but we did that without assuming similarity of the hypotenuses. This proved. We did it without even assuming that. We pretended, hey, we don't know. I don't know what C is, but when I find it, I hope there's similarity. There's all kinds of similarity, as there indeed is all kinds of similarity in triangles. The similarity of triangles is very, very, very prevalent. It's not the right word. I mean, it's just there's similarity within triangles. When you're comparing two different triangles and you look at what's going on within each triangle, there's a lot of similarity that we can talk about, and a lot of ratios that are equal across where one triangle is all the way to the other triangle. The two triangles compare to each other very, very much. Both when you look at them each by themselves, within themselves, and compare it to the other triangle, each triangle compared to the other, and across the triangles. For everything, for all three sides of similar triangles, regardless of whether they are right triangles or any kind of triangles where we can bring right angles in there. But notice, we just didn't play too. I didn't want to say, oh yeah, by the way, this hypotenuse C divided by B, this long hypotenuse divided by the second longest hypotenuse, is the same as the very longest hypotenuse C divided by the second longest hypotenuse, because they're all similar triangles. C divided by B, first longest hypotenuse divided by second longest hypotenuse, is equal to the second longest hypotenuse divided by the smallest hypotenuse. By the way, that's true. They are like that, but I never drew that conclusion. C was not to be found in here. C was not to be found in here until right here. Just right here. When we first say, hey, look, man, you got to say there's a base. There's a base length and there's a base height, and that's the same as this times this. That was the big thing. So you get to here, you're set. Square both sides if you want. That's neither here nor there. You already know we're done. All right, stuff. All right, guys. It is all right stuff, and it's all right, guys. This is very good stuff. I mean, it's neat stuff for us. So if it's there, if you want to look at it, it is there for you. And thank you for all your time.